So welcome to lecture number 13 and the last lecture. So today we will continue talking on about these neural networks and this back propagation, which we did last time. But last time, I'm using this chain rule. I just did it for the one-dimensional case. So today I want to sketch the general idea. If you have an actual neural networks where you have a lot of neurons in one layer, and then these weights are not just numbers, they are matrices. So one needs to talk about the derivative with respect to a matrix. So this we will do first. And then in the end, I want to go through a simple example using a library called TensorFlow, where all these things are already implemented. And then we will use this so-called MNIST data set, which is the data set which contains pictures of handwritten digits. And we will use this to train a neural network and then see how this works. And then there's also the so-called TensorFlow playground, which was suggested by one of you last time. So this I will also show there. So this is a tool in a browser where you can play around with neurons and then see visually how a neural network gets trained. Okay, so let's start. So again, I will recall the notations for those who maybe didn't attend last time. So a neural network, we have these different layers. So usually R denotes the number of layers. And for each layer, we will have a weight matrix and a bias vector and an activation function. And then there's a so-called linear part in one layer, which we denote by Z. And these brackets here denote the layer. And this linear part is given by multiplying the input of this layer, which is always the output of the previous layer, with a matrix, and then add a vector. So this will be the linear part, which in general is also a vector. And then the output of this layer, which we denote by A, is given by applying the activation function to each entry of this output. And so this notation I will also use later. So if we have this function here, this activation function, which is usually from R to R, I will also use this notation applying this function to a vector, by which we mean just applying it to each entry of this vector. Yeah, so there are a lot of letters, W, B, sigma, Z, and A, but I hope it's clear how they are related to each other. And then, for example, we had this explicit example where we had one input layer here with 5 neurons. So this A0 was a vector of size 5. And then in the first hidden layer, so the first layer, which was not the input layer, we have 3 neurons. And therefore, this weight matrix in this case is a 3x5 matrix, because we want to multiply this vector here with this matrix, which will give a vector of size 3. And to this, we will add this bias, which is also a vector of size 3. And this will give the linear part. And applying the sigma 1 to the linear part will give the A1, and the A1 has also size 3. And this will be the output of this layer, which then gets multiplied with this matrix here, which is a 2x3 matrix, and so on. And in this example here, we just have one output neuron, which, for example, could be to just decide a yes or no question in this case. Okay, but later in the example we will do in TensorFlow, we will have 10 output neurons here in the output layer, and each of them will stand for the percentage that a number is inside the written input picture. So the input will be a picture. It's a 28 by 28 pixel picture. So in total we have some 700 something input neurons. And the output will be 10. And then depending on which is the largest number in the output, this will tell us what number was in the input. Okay, and then last time we started discussing on how to train this network here. So in the first lecture on neural networks, we explained this way here, how to given an input and given these numbers here, we can calculate the output. So this is the path forward. And but of course the main question is how do we actually get these numbers here? And for this, because this is an example of supervised learning, we need some training set. So in general, if our neural network is an approximation for a function from Rn to Rm, then a training set is just a collection of tuples where the first entry is something in Rn and the second entry is something in Rm. And we want to train so we want to find these W's and B's given these training set. And for this, we will need to choose a cost function, and the cost function will check how good our current W's and B's are, giving this a training set here. Yeah, and then we discussed that in the lecture before, in the weeks, we already discussed cost functions. So in the first lecture, we had this example of linear regression, where we also considered a cost function. So there we had some hypothesis which depended on some vector theta, and in this case, this theta were the parameter we want to train, and the cost function was then a function in this theta. And for each training set, we took the sum over all trainings examples here, and then measured the difference between the hypothesis given this input of this trainings example to the correct output. And if this would be a perfect function, then all these things here would be 0 and the cost would be 0. And then we also had this other example in this logistic regression, where we had this example with this passing an exam, and there this cost function looked something like this. And yeah, and then in these cases, in all cases, what we want to find is, of course, the minimum of these. We want to have the minimal cost. And then there's this general idea of this gradient descent. And also here, a comment on this number n. So later in the example we will do, so in the lecture what I always did so far, I took the sum over all trainings example, but in reality you usually don't take the sum over all. What you do in most cases is you put it into so-called batches. So if you, for example, have 100 trainings examples, instead of taking always the sum over all 100, maybe in each trainings step, you will maybe just take 10 of them and then have a sum over 10 here, and then take the next 10, optimize again, and so on. So in this picture here of this gradient descent, this visually means that, this is a cost function, which is a sum over all trainings data. But in each training step, instead of taking the perfect direction, if you divide it up into small batches, then maybe you will do smaller steps, which maybe do not go in the direct direction, but they are somehow faster to calculate. So in the end, you do more steps, but in the end, you will also end up in this minimum here. And yeah, so maybe this gradient descent, I don't need to explain again. So the general idea is we start with some random parameters, and then we calculate the gradient, meaning we want to calculate the derivative of the cost function with respect to our parameter, because this is the entry. These are the entries of the gradient, and the gradient shows into the direction of the steepest ascent. and we want to go in the other direction to make our function smaller. And therefore, we have this update here. If I have the current value of our parameter, I subtract the gradient with some factor alpha, where this factor alpha is the so-called learning rate, telling us how somehow it's the rate of, well, like the name says, it's a rate of learning. So if this factor is large, then we do big steps, and if it's small, then we don't change our mind on our parameter so fast. Yeah, and it's we saw in some examples that it's not good to choose this too big and also not too small. So if this alpha is too small, then we are maybe too slow and it takes a lot of time. But if alpha is too big, then we can maybe jump over these minima because our steps are too big. So it's there's a not easy choice to make in choosing this alpha, and this probably depends on the application you are considering. Okay. Yes, and in our case, we have a lot of parameters in our neural network. In the example of the linear regression, we had this theta, and maybe this was the number of thetas were not so big. But for example, already in our small example with our 4 layers, we saw that counting all the possible parameters, so the entries of these matrices W1, W2, and W3, and the biases, the entries of the B1, B2, and B3, summing everything up, and we had in total 29 parameters. So the cost function in this case is a function from R29 to R. Yeah, but notice that the cost function is always a function to R. So we will never have a cost function which lands in R2 or something. Yeah, because it's always a real number which tells us the cost. And in this case here, so we want this gradient here. So we want to see the dependency of this cost function on each of these parameters. And but this, in our case, these what we call theta here now, they actually correspond to some entries of matrices. So what I want to make sense of today is something like this. So for example, I want to see what I mean by, or maybe so I mean these 29 numbers, for example, we had this W1, maybe let's go back here. So W1 was a 3x5 matrix. So these are 15 numbers. So somehow the first 15 entries here in this vector correspond to the entries in this W1. And therefore we can think of this vector here of being a vector of size 15, but instead of thinking as this as being a part of this vector here, we can also think of this just being a matrix. So here, this is a matrix of size 3x5. And we want to update this later by subtracting alpha times the part in the gradient. So we can somehow take these 50 numbers and just consider them as a matrix itself. So this here will be also a matrix of size 15. And then in the update, we will subtract from this matrix, we can subtract alpha times this matrix here. So the entries of this matrix, this just will be the matrix, where in this top left corner, so let's say this matrix here has the entries, let's say L11, L12, up to L15, and here L31 up to L35. And here, what I mean by this expression here, so this is a function from R29 to R. So it depends on all these numbers here. So when I say I take the derivative of this function with respect to this matrix here, then what I mean is just I take the derivative of this function with respect to the first entry up to here, this entry here, partial L35. Yeah, and these are basically, in this picture here, the first 15 entries of this vector here. But as we will recall in a second, we saw that we will not calculate them all at the same time. We will start at the last layer. And then for the last layer, we consider the parameters in the last layer, so this WR. And therefore, we will first calculate this for the derivative dj or partial j or partial WR. So this will be a matrix, and then we can update this matrix by subtracting this. But in the calculation of this matrix, we will save some numbers, which we then can use later to calculate the derivative with respect to other weights. Yeah, and this was the main idea of this back propagation, which I want to recall now. So, so the main idea of this was the following. So we have some training set, and we learned that given some input and we have some random starting values, or we have some current values for W and B, we can put this input here into the neural network, and then we get an output AR. And what the cost function does is, so here I can put some x1 here into the neural network, and for this x or xj, let's say some xj, I get some output, and the cost function takes this output of this xj and somehow compares it to the yj. Yeah, so there are different ways to do this. For example, it could take the difference of this number, and then maybe takes the norm or takes the square, whatever cost function you do. But the input of this cost function is always the output of the neural network, given the input as an input, this corresponding trainings feature, and this corresponding trainings label. So this will always be the input of the cost function j. And so, as I said, what we want to calculate, so what we want are the derivatives of this cost function with respect to these numbers which we are looking for, because these are the entries of the gradient. So we want the partial derivatives with respect to these matrices, and we want the partial derivatives with respect to the bias, where I goes through all layers. Yeah, and then, so the main idea of the chain rule was now that the derivative of this here, for example, so let's take, for example, the derivative of the cost function j with respect to the matrix WR. So WR is here, and the relationship between the cost function, where the first input of the cost function here is AR, and AR comes from ZR by applying the activation function, and that R depends on WR. So therefore, the relationship between J and WR is going this way here. And if I would like to have the derivative with respect to R minus 1, then I would go this way here. And we see that these two ways have a common path, namely this part here. And so this I will make precise later, but I mean, this we did last time, that this here will be something we can save, because this will be needed to calculate the derivative with respect to this. But this we can also use later to calculate the derivative with respect to this. And doing this, we can save this part here, which we can then use later in the step to take the derivative with respect to a w before. And the relationship is by using the chain rule. So taking the derivative of this with respect to this here means I can take the derivative of this with respect to AR, and then I can take the derivative of A with respect to Z. And then here I can take here's A, sorry. AR, and here I should write ZR, and here ZR, I want the derivative with respect to WR. Yeah, and some of these parts are easy to calculate because here's for example, the derivative of A with respect to Z. This is given by this function sigma. So this here will basically just be the derivative of the activation function. Yeah. Okay. So, but and yeah. So, and this part here is what we will. So this part we can save for later, because this part will also appear when we want to calculate the derivative with respect to this, because then we would go all this way here. But we can go directly the derivative of J with respect to Z, and then to ZR, and then derivative of ZR with respect to AR minus 1, and then AR minus 1 derivative with respect to ZR minus 1, and then ZR minus 1 derivative with respect to WR minus 1. But in this part, then we will also calculate this here, which we can save. And then if we want to calculate the derivative with respect to WR minus 2, we can start directly taking the derivative of J with respect to ZR minus 1, and then go here. So these parts we then don't need to calculate again. And therefore, these steps we want to save, we will give a name. So this part here, we will denote by delta. In this case, this is delta R. So by delta R, I mean that del J, the derivative with respect to that R. And therefore, this here, somehow, this will be delta R minus 1. And this will be the derivative of J with respect to that R minus 1. Yeah, and maybe the confusing part is now that these are, in general, are not numbers. Some things are matrices here and some things are vectors. And that's why I want to make an explicit example now for the first part here. So this ZR is always a vector. And therefore this thing here, so this delta R is also a vector of the same size as ZR. And the entries of this vector are just the derivatives of J with respect to each entry of this Z. So if Z is a vector of size 3, then this delta R would also be a vector of size 3. And the first entry is just the function J, taking the derivative with respect to the first entry of ZR, and so on. Okay, but let's make this precise. So this here is the same picture as on the slide before. And here, this is the notation I said, this delta j. By this, I always mean the derivative of, well, capital J. Maybe that's not a good notation. And with respect to that j, so these are always these steps here. Yeah. And now let's do an explicit example where this here, that R, is in Rm. So this means that BR is also in Rm. And let's say that these A's in the step before are in Rn. So this means that this here is also in Rn. So this means, what is the size? I mean, this is what I'm writing here. And this implies that this size of this matrix here is an m by n matrix, because this vector here is given by multiplying this matrix with this vector. So if this is an m by n matrix, then I can multiply it with this vector of size n, and I get a vector of size m, after I also add this vector of size m. And now the claim is, so the thing we want to show is how to calculate these deltas, and how to calculate these derivatives with respect to WR. Or in general, I mean, what we want, so recall, we want in general, we want the derivative of our cost function with respect to our weight matrices. And we also actually want this with respect to our biases. But if we understand this, then this part is actually easier. And the general claim are these two formulas. So in each step, we want to calculate these delta j's. And the claim is that in general, a delta j can be calculated by this formula. And then having a delta from this in this step, then we can always calculate this, this derivative we want by just multiplying this delta, which is a vector, with the transpose of this A, which is a vector. So in this case here, so I mean, what is this delta R in this case? So delta R is del J del that R. That R is in Rm. So delta R is also in Rm. So, but maybe let's make clear what this means. So this is a cost function. The first entry is a cost function where I take the derivative to the variable ZR1. So the first entry of the linear part of the last layer up to del J del that M R. So this here is a vector of size m. So this here, if I have a vector of size m, so this here is a vector of size n, and this here is now the transpose of this vector. So this here is a vector of size 1 times n. So this will be an m times n matrix. At least the size of this matrix here is what we expect, because we want here the derivative of the cost function with respect to WR. And what this means, I mean, if WR, well, this we had before, has some entries L11 up to blah, 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 then this, and if this is an n by n matrix, then this derivative with respect to this matrix, by this we mean we take the derivative with these entries. So this has the same size. Yeah, so at least this formula here gives the same size. And so this I now want to, so this part here, maybe want to calculate. So why does this formula hold? So why should we take the transpose? So somehow for numbers, like we did it last time, if everything is, if m equals n equals 1, then everything are just numbers. And then it's somehow clear that, well, first, if these are numbers, then this is just a linear function here, number times this. So if I take the derivative of this here with respect to w, then of course I just get the number a. Yeah, but the transpose of a number is just a number. And then this del here is just the derivative with respect to zr. So therefore this here is exactly just the chain rule that to take the derivative of j with respect to w, I just multiply the derivative with respect to z times the derivative of z with respect to w, which in this case is just the number a. Yeah, so this is what we did last time. But now in this general dimension setup, one needs to be careful a little bit with matrices and vectors. So we need to see why we need to take the transpose of this vector here. Yeah, so let's, I think I have a page here. Page. Huh. So yeah, so and for this we need to see what so we want to calculate this. So this will be a matrix. So we can ask how does the entry in the ith row and the j's column look like? Yeah. And for this, maybe first, what is that r? Or maybe now I don't use, so maybe just, oh, well, I will write r. AR minus 1 plus b. So what is this? Well, I have here the matrix. This has some entries with some wij. Well, maybe here I should also write r. And I multiply it with this vector here, which has some entries up to ar minus 1n. And I add this vector 1 up to b r m. Yeah. So what I want to see is what is, if I take the derivative of this z with respect to the entry wij r. What is this? And or more precisely, what no, I'm confused myself. Yeah, I mean, first, where does this entry here for a fixed ij where does this appear? Well, it just appears here in the ith row and nowhere else, right? So the only place where this variable appears is here in the ith row, and there, who do I multiply this with? Well, if I multiply the vector a, then I will take the j's entry here, because this here is in the j's column. Here's the j's column, and therefore I multiply this number here, wij, with the number aj. Yeah. And the rest doesn't have any w. And here I add the b and also other stuff. But since I will take the derivative with respect to this wij, everything else which do not depend on this will disappear. And therefore, if I take the ith entry of this function z, the derivative with respect to this entry, this is exactly ajr. Yeah. And and this here, the thing we want using the chain rule is, well, it's here I have ij. So this here is what I just calculated. Yeah, I mean, first of all, I now want to have the entry here in this matrix at the position ij. So therefore, I need to take here the only contribution is the derivative here with respect to zi, and that because the others, they don't give a contribution here in this ith row. And this here, by this observation here, the derivative of this row with respect to this entry is exactly this aj. So this here, the second part is ajr. And this part here is the ith entry of the derivative of j with respect to z. And this is exactly, if we take our delta, this is the ith entry of our delta. Yeah, because the delta is defined to be this vector, which as entries has these partial derivatives. And therefore, the statement is that this entry here, the entry in the ith row and j's column, is given by multiplication of the entry in the ith row of this delta times the entry of the j's entry of a. But this is exactly this statement here, because this here, if I write it down, I have this vector delta 1 up to delta m. And here I have this vector a r minus 1, 1 up to a n r minus 1. So this here will be an m times n matrix, and the entries of this matrix are exactly this, because here in the j's column I have exactly the entry of the j's entry of a, and in the ith row I multiply exactly the ith entry of this delta. So therefore, this matrix here, the matrix which contains the derivatives of this j with respect to the w, is exactly given by this product of this vector here with this vector. Yes, and this gives this matrix. Yeah. So again, the derivative of this here with respect to this, which is a matrix, is given by multiplying the matrix which comes from here, so this delta, times the transpose of this thing here. And with the same argument, you can show that this is also true if you would do it with respect to this here. I mean, I now just fixed the R because I gave these numbers here a name, but with the same argument, the derivative of J with respect to WR minus 1 is given by the vector del R minus 1 times the transpose of what I didn't write here, the A R minus 2. It's with the same argument. So you can always, if you have the delta, you can obtain this here by multiplying with the transpose of this A. So and this A is just the output of the layer before. Yeah, and these deltas are exactly what we will save in each step. And we see here the reason why. And in each step, these deltas can be calculated by this formula, which is a similar idea. So, for example, here, this here would be what I denote delta R minus 1. So every time I mark something like this, by this I mean the derivative of the start point with respect to the end point. And the statement here is that I can take the delta before, so this delta here, and multiply it with the transpose of W. And why? Because this Z here depends on this W. And what we want to do is we want to take the derivative of this here with respect to A. And therefore, with a similar calculation, you can show that if you take the derivative of this guy with respect to A, what you get as a factor has to do with this W. Yeah. So if these are numbers, then this is again clear. But here, with a similar argument as we did here, you need to take the transpose of this, because now it's not a number anymore. It's in this case, it's a matrix. So this part here corresponds to the derivative of this part, because it's a connection of this derivative, this delta, and the derivative of Z with respect to A, which is given by W. And then from A to Z, we have this activation function here. And this here just means a pointwise multiplication. And then therefore the pink part here is built up of these parts here. So this is basically again the chain rule. So maybe let me use more color to make it more confusing. So this orange part somehow is here. And then, well, the whole part is pink. And somehow here, this part is this thing here. And then to calculate this, the derivative of J with respect to this, we can use again this formula here. So then we take the pink part for this here and just multiply with the transpose of the A coming from there. Yeah, and this is in general this back propagation, where we can in each step save our deltas to use it in the next step. Okay, and this is the general algorithm. And maybe with this, I hope it becomes clearer. Oh, here I actually saved space to write this down. Anyway, so then we see that this, what I wrote down last time, maybe becomes clearer. So this was stolen from the lecture notes of the Stanford lecture, where this algorithm is now described in general. So we start at the last layer at R, and the first thing we calculate is the delta R. Yeah. So actually, this I didn't do. So what is delta R? Well, delta R is del J ZR. So let's well, basically it's the J with respect, the derivative of J with respect to AR, and then AR with respect to ZR. So usually, so this here will correspond to the derivative of the activation function. And this here will depend on how the cost function depends on A. So for example, if the cost function, which as an input gets this AR and a trainings example, so it could, for example, be, so if I take here the J's trainings example, and let's say the J's trainings feature gave this AR, then, for example, I could take the, for example, I could take the least square by taking, for example, the norm of these two vectors. So this could be, for example, one possible cost function. So it's the sum of the squares, and maybe in this case I square this and take 1/2 or something like this to make the derivative easier. But this is would be one possible example, and then the this part here would be a vector where each, so if this here has size m, then this part here would be the derivative of this expression with respect to the entries of this, which in this case would be actually just the entries A of A. Yeah. Okay. But in general, so for example, if you have a little bit more complicated cost function like we had here, then of course calculating this is a little bit more involved. But the example I did basically corresponds to this here. Okay, and so then let's copy this claim here and compare this with the slide I showed last time. But this is exactly now what this algorithm here does. So it starts by computing this delta R, which is the cost function with the derivative with respect to ZR. If we are in the first step, so at the rth layer, and then the derivative with respect to our weight matrix is exactly this here. So this is what we did. And so what I didn't do now is the bias, but it's a similar idea, but the bias is simpler. So in this case, I don't need to multiply with an A because the bias is just here alone. So I wouldn't need to multiply with some factor. It's just the factor I have here is 1. And therefore, here I really just have the delta, and I don't have a number here because B, the dependence of the Z on the B is just by a factor of 1. And then if we are not in the last layer, the computation of this delta is given by this formula here or by this formula here. So in their lecture, they fixed an activation function. So they use this rectified linear unit. But in general, this here will be just the the sigma, the derivative. Yeah, and this here is pointwise multiplication. So this here is a vector where in each entry, maybe I can make this a little bit clearer. So this here is a vector when each entry I apply the derivative of sigma to the entry of this of these sets. Zk. Well, now I don't know the size of this, but let's say it's size n. And then this here just means this here will also be a vector. And this here just means I multiply this entry with this, I multiply this entry with this, and the output will be also a vector. And this will be the delta. Yeah, and then this can be used. So this here will be a matrix. And then in this gradient descent, I will take what I do is in the update rule, the old W at some layer J, I will define as, so the new W is the old minus alpha times, and then I subtract this matrix here. So this will be the update rule for the W and similar for the B's. And doing this a few times will then minimize, or at least make it smaller, the cost function. Okay. Are there any questions on this? Maybe it's hard to understand at the beginning and a little bit confusing, but I think the easiest way to understand is really make yourself a small neural network and then really focus on the dependency of the cost function on one entry of some weight matrix, and then see what is the derivative with respect to this one entry. So this is really a classical function depending on one variable, and then see how can you calculate the derivative. And then you will see that these formulas make sense. But it's now written in a compact form and using matrices and vectors. But I think this is just a notational confusion and nothing else. And maybe those familiar with Python could try to implement this. So this is what I would like to say next. So, I mean, this is now the last lecture of this course, at least for this semester. And there are a lot of things we couldn't cover. So, for example, there's this notion of convolution in neural networks, which are used for image recognition. The basic idea is that that you somehow weight certain parts of a picture with a filter matrix and do some, to say, for example, edge detection and things like this. So there's a notion of the so-called convolutional layer, which work a little bit different to the usual layers we discussed in this course. And also what we didn't discuss at all, because I'm also not an expert in the field, is how to choose actually your neural network. Should I use as much as possible neurons, or how many layers should I choose? So this is something which is important in the field, but which we didn't discuss at all. So how to choose the activation function, and in what scenario should I choose this activation function, in which should I choose this, and so on. And there are a lot of things we didn't do. And so, but what you can do next is maybe try to implement what we did by yourself. Maybe just fix a neural network, let's say 3 layers and two neurons, and then by hand try to implement, for example, this back propagation. And then maybe in the next step, what we will do after this slide, use libraries which already implement this, and then you can play around what happens if I have 10 layers compared to 2 layers with more neurons. And then there's also this this book, which is this book here, which is quite standard. So if you search for what is the book they recommend to read if you want to really learn deep learning, then often this book here is recommended. And this you can also find on this site here. And for example, in chapter 5, they talk about machine learning in general. And maybe after this course, you should be able to read this chapter 5 and at least see a lot of words which you already heard before. But of course, they cover much more than we could do. And yeah, but this can also get at the end quite technical. But I think if you really want to learn the theory, then this is really a good book. Because I think a lot of books more focus on programming and stuff like this. But in this book, you actually can find also the theory behind this. Okay, so here's this, I prepared a notebook. And this link I also put on the homepage, so you can find here the Colab notebook on the homepage. And this is a variation of, so there's the site here of the creators of this library TensorFlow, and they did well, they have several tutorials, and there's a quick start for beginners where they use this data set I will introduce in a second. And this I modified a little bit to have it more similar to what we did in the lecture. Okay, so let me go through this. So first of all, to use TensorFlow, you need to import it. And later I will also use NumPy. That's why I use it here. And then there's this MNIST data set, which is quite common to use. And this is already inside this TensorFlow. So if you want to use this, you can just get it here as inside this data sets MNIST. And so this contains a trainings data and also test data. So this trainings data is used to train the a neural network. And then with the test data, you can check how good you trained your data. So this test data here, you will not show your neural network in the trainings time. So these are really new things, and you will just use this trainings data to train your set. So these trainings data will be stored in the train. So this X train will be the features. So this will contain pictures. And here you see the shape is, so there are 60,000 pictures, and the size for each picture is 28 by 28. And I will also show it to you in a second. And the labels are just numbers between 0 and 9. And for this, I will just have an array of size 60,000. And yeah, so let's see. So again, we use this pie plot here. So for example, if I want to get the second trainings label, in this case here, maybe first let me get this. So here in the, for example, the second, or actually third, because we start counting at 0, this third trainings example is a number 4. So here this is a 4. And the corresponding data is now inside this X train 2. And if we just give this 28 by 28 array to this pie plot, then it will just plot this picture here. So you see here, this is the data inside this training set. And the entries of this X are between 0 and 1. So here you see, if after loading the data, they're actually between 0 and 255. So that's why there's this normalization here, which just puts them between 0 and 1. And for example, we can also see what's actually, if we just look at the numbers. So here you see this is a 28 by 28 array with numbers between 0 and 1, and the zeros corresponds to the dark color. And here, these colors correspond, or these numbers correspond here to the to the bright colors. Okay, so let me uncomment this. So we can also check, for example, what is in the third entry here. For example, this is an example of a 1. Okay, so now we build our neural network, and how is this done in TensorFlow? So we will first create a model, and by model you usually mean the geometry of your neural network. So how many layers I have. So the first layer here is so-called a flattened layer, which just means that this picture here, so this is a 28 by 28, and we will flatten it to make it a vector. So we make it a vector of size 28 times 28. Yeah, so this information here means inside it's actually a vector of size 784. But the input this neural network will get is usually a 28 by 28 array. Yeah, so we will have, in the first, we will just have a layer with 284 neurons. And then, so there we do not have an activation function because this is the input layer. And then the first hidden layer, we just choose a layer with 128 neurons. And here you can see, we can say which activation function we want. And in this case, it's the rectified linear unit. Yeah, and if you want to know what kind of activations functions are there, you can, for example, layer stands, or maybe let's go here. So this is a dense layer, and dense layer just means that this the neurons get input from all neurons before. And here you can see a lot of information, what you can change. And probably somewhere here you can also get an overview of the activations. Yeah, so so for example, here's this rectified linear unit. For example, here's the sigmoid function, which also appeared in our, but you see that there are a lot of more. Yeah, so here you could also change the ReLU to sigmoid or something else, or maybe you write your own activation function, which can be used there. And then here the last layer where we don't use an activation function, which in this case it now just means it's the identity function. The output layer will be a layer with 10 neurons because we want for each number an output. Okay. Yes, so this is our neural network. And now we need to choose our loss function. And here's now a loss function I didn't discuss. It's a so-called cross entropy. But we could also, for example, choose our mean square error function. But if you play in this example and you use this mean square, you will see that the results are much worse. We will see maybe in a second. Anyway, let's make our model. And maybe let's not...
remark here.
Yes, please.
Cross entropy is just the negative of your log likelihood.
Oh, okay, then we had this in course. Thank you very much. Yeah, so then we had this... oh, thank you. I should have looked this up. Thank you very much. So this is what we had then. And but maybe let's not train this yet. Let's maybe just see what the neural network does when it's not trained. So here for this, so there, if I have this model, I can predict what the neural network thinks of some input. And here, in this case, we can give this all the input, the test data. So recall we have training and test data, and the test data are not inside the training. And so the output will be a vector, and we want to see the maximal output. So for each number, it will give a percentage, and we want the maximum. So in this case here, this here will just tell us. So here, this I will just tell us what thing we check. So let me just show you. So for example, in this case, this is the picture we have in the training set at position 20. And now the neural network predicts that this is a 1. Because we didn't train the neural network yet, so the output here is usually wrong. So this is not a 6. But now let's see what happens if we train this. First, after choosing the loss function, we can then give our model here the loss function and also the way how it should optimize. So here this SGD is exactly what I described, this standard gradient descent. And then we can train our model, which is done by this function fit. So we give it the training's features and the training's labels, and then how many episodes we want, and what I mentioned earlier, these batch sizes. So instead of going over all 60,000 training sets at the same time, it will go at over 32 at one time, and then update the weights. And then it will take the next 32. So each of these episodes of this epoch are, they have 1,875 steps, because this is these 60,000 trainings data divided by 32. Yeah, so let's run this. So you see here in the first episode, for each of these steps, you will see how long it takes. And here you can see the loss function. So at the beginning, the value of the loss function is 1 point something. And then after the first episode, it's 0.3. And it goes down to this, which is maybe still not really good. But so let's see now what this thinks now about this here. So now in this case, it predicts that this is actually a 1. So let's take some other example. In this case, it also predicts a 1, which looks correct. Oh, this was too much, sorry. So here we just have 10,000. So, and here, for example, it predicts this is an 8. Yeah, and of course, this you can, in general, you can check how good you did. So there are some functions which which checks all the test data and gives you a general measure how good your neural networks got trained. And for example, if we would change the loss function here, I think for this I should try this new.
Sorry, Professor, did you just change the loss function?
Yes, I just now changed the loss function.
But you have 10 outputs here. The dimension doesn't match.
What do you mean?
Oh, I see. Okay. Okay, so for Spears's categorical cross entropy is actually making a one-hot vector from the number of category. But with the mean square error, you are actually comparing 10 numbers with 1. So if you want to use mean square error, I think you have to change the number of neurons at the output layer from 10 to 1.
Or because the y's are just one number, and
yes.
I changed. Oh, I see. So I should change maybe just the the training set make a vector. Oh, I see. So maybe that's. Well, I could also make the training features to be a vector, right? Of where, so now I have a number, but instead of taking the number, I would put a 1 in the vector at this corresponding position.
Yes, actually, that is what the word sparse in your loss function do.
Yes.
And another thing is actually your network was not output the probability, but only a number corresponding, and is positively related to the probability. It was not normalized.
Yeah, but in this case, because I just take the maximum here, this doesn't matter, right? If I normalize this.
Yes, it's fine, but it's no longer the probability.
Yes, so yeah, for this, yeah, I could use a softmax, or I would normalize this. Yeah, but yeah, so if I just care about which class this is, I can just take the maximum here. Yeah, but thank you very much. But then I'm wondering if this is not automatically done, what he actually does here in this case. What does he calculate?
Actually, it takes the average of your 10 outputs.
Okay, so then that's terrible. I see. Okay.
Actually, I think maybe it's fine. Maybe it's actually better than one output because you will have some dead rule if that's the case. Oh, actually not.
But anyway, I think in this case, the result is terrible. But maybe this then. Okay, so thank you very much for your comment. So I should have thought more about this case here. But yeah. Yeah, so actually, if we don't reset this and just do this again, then we will start. So at the one before, so it's just getting better and better here. Okay. Okay. Yeah, thank you for your comments. So, but yeah, for the others, please play around with these, maybe add more or less layers here, and maybe go to this page here where they do a lot of examples. And of course, you can find several examples online. But there, for example, several data sets they provide, not just this MNIST, but also other types of data sets you can play around. So there's this Titanic data set, and so. But maybe from your research, you have maybe some of your own data you can try to use in some sense. Yeah. Okay, so this is this. And another thing which was suggested by one of you, which was a nice idea, is this so-called playground, the TensorFlow playground. And so here you can visualize a neural network, but maybe at the beginning it's a little bit confusing. So here the input of this is a vector of size 2, and the output is, so it's a classification problem here. The output is, in this case, -1 or 1. So here on the left, we can choose the training data. So for example, here we have some training data where we have these blue points in the middle with the value 1, and the orange points in a circle outside. And what we want to train is to assign to a point in R2, or in this square here, we want to assign a color. And in this case, what we want is that the guys in the middle get the value 1, meaning the color blue, and the ones outside get the color orange, in this case -1. And so, and here you can choose the input. So I said we have, well, the original data, the input is vectors of size 2. And so this basically would mean that we choose the x1 coordinate and the x2 coordinate. But here the option is that as an input, you could also choose the x1 squared coordinate. So this is similar to what we did with linear regression. If we just take the original data as input, then this is for the approximation of a linear function. But as a feature, I could also take squares or cubes, and this, for example, then gives an interpolation for polynomials. So the similar idea is somehow here, instead of just saying I have a point in R2 with the coordinate x1 and x2, as an input, I could also give x1 squared or x2 squared or x1 times x2. And here you can choose layers. So here now it's a hidden layer with just one neuron. And here these lines are exactly the weights. So here the input is, so this is our A0, so to say. It's the first entry and the second entry. It's a vector of size 2. And here we just have one neuron. And therefore here the weight is a 1 by 2 matrix, which has 2 numbers. And here the colors, actually I think it's a little bit confusing because these minus and -1 and +1 have different meanings in different diagrams here. But here the colors on the line corresponds to the value of the weight, to the entries of our matrix. And here we can choose an activation function, a learning rate, and here, well, it's a classification we choose here. But anyway, let's try to match these trainings data here with just one hidden layer and one neuron. And here, if we press the play button, it will train on the neural network. And here you can see trainings loss and the test loss. And here's a ratio between trainings data and test data. So there's a lot of data points. And here you can choose how many of them should be trainings data and how many of them should be test data. And then you can see here that the trainings loss, so the loss for the trainings data is this, and the test loss, so for the ones which were not used in the training, the loss is this. So of course, always this. So this loss should be, in general, be bigger than this one here. So you see in this case, with just one neuron, there's not really a good result here. So the result here is now that this neural network, if a point is on this side, it will get the value -1, and if it's on this side, it gets, well, in this case, something around 0. So let's add more neurons here, and let's see if we just change the number of neurons, how the output will change. And here we can see now that this is doing much better. We see that really he can recognize that there's that in the middle, the value should be a +1, and outside it should be a -1. Yeah, so you can play around here, and you can also see how these neurons work. So for each input here, you can see the value of this neuron here. So if I have a point somewhere here, then this neuron as an output will give a something -1. And if I have an input here, then this means that this neuron in this case will give something with a +1. So you can somehow see how these neurons react to an input by just looking at this picture here. And you can also see how the interaction of the input here, the x1 coordinate is for this neuron, and for this neuron. But yeah, so here you can find some explanation of this, and you can play around and add more layers here and more neurons, and maybe change your activation function. So for example, here, if we choose rectified linear unit, then you will see that the color orange disappears because rectified linear unit just gives positive output. So of course, these will now just give output which is not negative, and therefore now we don't have any orange here in these pictures. Yeah, but here you can choose different data, and here you can choose how the relationship between training data and test data is, and also the batch size and noise. You can make them a little bit more spread, and then it gets harder for the neural network to actually find something. But yeah. Yeah, I think it's a nice tool to visualize. So thank you for the suggestion. But I also think that the creators should have distinguished between certain colors here, because at some point, at least for me, the +1 and -1 somehow live in different worlds, so they shouldn't have the same color. But anyway. Okay. I think that's all for today, and maybe for this course. Or maybe I will stop recording, and then you can ask questions.